Previous lectures we studied transverse vibration using influence coefficient method and transfer matrix method. In these two methods, the shaft which we considered was having only the elasticity property, but in some cases the shaft mass is not negligible, and we need to consider the shaft stiffness and mass property simultaneously as a distributed property along the length of the shaft. And for such case we need to model the shaft using a continuous system approach. In continuous system approach, as we have seen in the torsional vibration case also, that each and every particle of the beam is independent of each other, and a continuous shaft is having infinite degree of freedom. And for when we model this kind of system, the differential equation, the governing differential equation, generally it becomes partial differential equation. So when we are considering only the one dimensional model of the shaft, so generally we will be having the differentiation with respect to time as well as spatial coordinate, that is along the length of the shaft for 1 degree of freedom system. And for the present case we will be considering the simple one dimensional problem, not one degree of freedom, but one dimensional. So in this only the property of the mass and elasticity will be changing along the length of the shaft. And in this particular case, we expect the calculation of the natural frequency and the mode shape will be more accurate as compared to when we consider the shaft as massless. And generally this is the case when shaft is relatively thicker. In this particular case, we will be considering the Euler-Bernoulli beam model, which we generally study in the strength of material Euler-Bernoulli beam model. And not only we will be obtaining the natural frequency and mode shape or eigenfunction, also we will see how the force response can be obtained using this eigenfunction property along with the orthogonality property of the eigenfunctions. So let us see what are the things we will be covering in this lecture. So basically we will be dealing with the continuous system approach for transverse vibration. Free and forced vibration analysis we will be doing for simple cases. So various concepts like boundary value problem, eigenvalue problem, eigenvalue and eigenfunction, orthogonality condition, modal analysis. So these will be covering in very briefly. I will not go in much detail on this because our main focus would be to use this model, continuous system model, for finite element formulation, which is having more versatile application. So with this as introduction, so let us see how the continuous system model for transverse vibration we can able to do it. So if we have a shaft, this is the axis of the shaft, and one of the, let us say we are considering one of the plane, and in this we can have some kind of distributed load or distributed force onto this particular beam, which is function of z. So this is the force per unit length, or we can have concentrated force at some specified location, let us say z0. Now if we want to analyze a particular plane, let us say a plane which is perpendicular to the axis of this shaft. If we see this particular shaft from side, maybe any cross section we can take. For this case we have considered let us say circular cross section. So, we have coordinate x and y here. So, during bending of this beam, generally we consider this particular plane, and in Euler-Bernoulli beam hypothesis, we assume that this particular plane remains plane after bending, and this is the elastic line of the shaft, and always it will be perpendicular to the elastic line of the shaft. So, that if it is bending, this is the elastic line of the shaft. So, this particular plane will be perpendicular to this elastic line. Also, it will be it will not distort, it will remain plane after bending also. So, this particular hypothesis will be using it, and in this particular case Euler-Bernoulli beam, when we are applying forces in let us say y direction, there will not be any displacement in the x direction would take place. So, as such there is no coupling, elastic coupling between the force and the displacement in two directions. So, if we are applying force in y direction, displacement will take place in that direction only. In this particular case, the displacement, as we have seen earlier, there will be linear displacement and the slope of the beam. So, we will be having two coordinates will be required to define the displacement of this particular shaft segment. Now, let us try to obtain the free body diagram of this small segment. This is at z location, and we are taking a small strip of thickness dz, and we are taking the free body diagram of that, and we are applying various shear force, bending moment in this particular system. So, let us take the free body diagram of this. So, this is a shaft segment. We have shear force in this direction, positive y direction. Shear force on this plane will be changing because we have distributed property of the mass and stiffness. Also, we can have some kind of load, external force here. So, this shear force is changing, and this will be given as this. Similarly, the bending moment, this we are taking positive conventions. So, bending about x axis, other plane, it will be again it will be changing to this value. So, two planes, they have different bending moment and shear force, which we have represented like this. Now, apart from this, this particular distributed force I have applied, and this is per unit length of the shaft segment. So, total force will be this force into the dz. So, if we take the, let us say, moment balance. So, if we are taking moment about, let us say, this point O. So, if we are taking counterclockwise direction as positive, so this moment balance mx, this is negative, this moment will be positive. Then moment because of the sy will be again negative, and will be having distributed force, and because of this we will be having, sorry, this is z distributed with respect to z dz. So, this is the force, this is acting at the middle, let us say, and the moment arm of this, if it is uniformly distributed, can be approximated like this. Apart from this, we will be having inertia force, that will be mass into, or mass per unit length into segment of the thickness of the shaft segment. So, this will be the mass of the shaft segment into into angular this linear acceleration. So, this is the inertia and it will act at the middle. So, moment will be this one, and because this is acting in the opposite to the y direction, so downward direction. So, it will produce a counterclockwise moment, positive moment, and this is equal to 0. In this particular case, we can able to see that some of the terms like this term and this term, they are carrying dz square term, because dz is small quantity and square of that will be further small. So, we are approximating this equal to 0, we are neglecting these terms. So, basically now you can able to see also this will get cancelled. So, we will get a relationship between Sy and dz minus Sy dz is equal to 0. So, even this will get cancelled. Now, we know that bending moment is given as EI del square V is, let us say, displacement, linear displacement, so dz square. So, this expression we can able to write it as del z EI can be function of z. So, I am keeping inside at present, minus Sy is equal to 0. Now, what I am doing, I am differentiating this whole expression by z once more, and because of that I will get del z square EI del square V by del z square minus del Sy by del z is equal to 0. So, this is one of the equation. This we obtain by moment balance. Now, we can able to do the force balance. For force balance, we have shear force and external force and inertia force. So, these we can able to equate keeping the sign. So, force balance Sy is in positive direction, Sy, and the change in that is in negative direction. So, this, and then we have external force which is distributed is this, and if we have concentrated force, that also we can able to incorporate in this. So, F naught, and we are using a direct delta function this. So, basically this will give us a concentrated force as distributed force over a very small length, and if we multiply this by dz, we will get the force, total force. So, this is basically distributed force per unit length over very small length, and into dz will give us the total force. This is the distributed force over finite length, but this is for very small length, and whenever z is equal to z naught, then only it will be having this will be having one value, unit value, otherwise it will be 0. And apart from this, yes, so this will be equal to m, that is rho a dz, that is mass of the shaft segment, and acceleration. In previous expression, when we derived the moment, so these were the moment equations. We equated this equal to 0 because in the Euler-Bernoulli beam we do not consider the rotary inertia in this. So, that is why we have not taken the rotary inertia here. With rotary inertia, if we are considering that particular beam is called Rayleigh's beam. There is a higher order beam, so we are not considering here, we are equating it to 0. So, but linear acceleration we are considering, and mass into linear acceleration we are considering in this. So, now we can able to simplify this, this will get cancelled. So, this will give us dy by dz is equal to minus rho a del square y by del t square plus external force, distributed force, and the concentrated force that z is equal to z naught. So, this particular expression we got is second equation. Now, you can able to see in the first equation we have this particular term. So, we can able to substitute this here. So, if we substitute this there, we will get an equation of this form. This term is as it is. Now, we are substituting this term. So, we will be having rho a del square y by dt square, and other terms I am keeping in the right hand side. So, this is the equation of motion of the Euler-Bernoulli beam, in which we can able to see this is the elastic force, this is the inertia force, these are external forces, distributed and concentrated force. And now we will try to solve this equation for free vibration. That means we will equate the external force equal to 0, and we will solve this particular equation. In torsional vibration case, we had the special derivative that is with respect to z as 2, but here it is fourth order derivative is there with respect to z. So, here the solution of this is more difficult as compared to the torsional case. So, we derived the governing equation for Euler-Bernoulli beam for transverse vibration. Now, we will solve a free vibration problem for very special boundary conditions, because this whatever the differential equation we got it, partial differential equation, once we are specifying the boundary condition, then only the solution of this differential equation will be unique. And that is why this particular problem, the differential equation associated with the boundary condition, is called boundary value problem, and this will be basically converted into a eigenvalue problem, and that can be solved for the natural frequency of the system. So, now let us see, this is the differential equation which we derived. Here I am using a notation of prime. So, 1 prime is representing that is derivative with respect to z. So, there are 4 primes. So, it is representing that the derivative with respect to z is 4 times, and the dot is representing the derivative with respect to time. So, is having twice the derivative with respect to time. So, basically we have prime as derivative, partial derivative with respect to z, and dot is representing derivative with respect to time. Now, if we assume the solution of this, we will be using the separation of variable method as we did for the torsional case. So, in this case we will take a function which is function of z alone and a harmonic function. In this particular case, now for free vibration this quantity will be 0, and the motion we expect as a harmonic. So, this particular function we are assuming as a harmonic function. So, if we derivate this assumed solution with respect to z 4 times, so obviously the first function will get derivated, this will not get derivated because this is function of time. Similarly, if we derivate this with respect to time, this harmonic function will get derivated twice. Now, the harmonic function will be having this form, in which this is the natural frequency of the system, and A and B are the constant to be determined from the initial condition of the problem. And if we derivate this twice, we can able to see that we will be having this relation, which is a relation for the simple harmonic motion. Now, if we substitute these assumed solution in the equation of motion for free vibration, we can see that we will get E I x x and this 4 times derivative eta t, and then this one is rho a, and this when we are taking the derivative with respect to time, we will be having minus omega n f square eta t is equal to 0, because we are considering free vibration. So, there is no force, external force in this. Now, we can able to see that this equation, because eta t is common, so this equation will give us equation of this form. And now, this equation, because in this particular case only the variable is z. So, this equation, which was earlier partial differential equation, will be now ordinary differential equation of 4th order, and this beta constant we have defined like this, which is coming from here. Now, we need to solve this particular differential equation using the boundary condition of the problem. So, till now we have not talked about what kind of boundary condition we need to apply it, but now for solving this we need to consider the boundary condition. So, general solution of that is this will be having 4 constants. So, not only sine, cosine, but their hyperbolic functions also will be appearing in this. In torsional case, we had only the harmonic function, not the hyperbolic ones. So, now we are considering a beam of simply supported end condition like this. So, in this we can have some kind of, there is no loading, but we can able to disturb the beam and we can able to analyze the free vibration of that. So, for this simply supported beam, we can able to see if we have this as z axis, this is y. So, here we have z is equal to 0, total length of the beam is, let us say, capital L, or the span of the beam is L. So, here we have boundary condition that the displacement will be 0 at both the ends, at x is equal to 0 and at x is equal to L. So, this is the displacement at 0 at both ends, and apart from this we will be having moment 0 at these two ends. So, basically this double derivative is representing the moment if we multiply this by constant E I. So, basically E I is constant. So, there is no meaning here if we retain it. So, we have removed that. So, double derivative of this at x equal to z is equal to 0 and z is equal to L are 0, because this is simply supported condition, which is representing a moment r 0 at these two ends. Now, once we have these boundary conditions, we can able to, we have 4 boundary conditions. In this equation we have 4 constants. So, we can able to apply the boundary condition in this problem, and we can able to solve for C1, C2, C3, C4. So, if we apply first boundary condition, this one here, if we put z is equal to 0 here, this will be 0, this cos term will be 1, similarly this will be 0 and cos will be 0. So, we got this term. So, basically this equation is C2 plus C4 is equal to 0 if we simplify this. Similarly, if we put x is equal to z is equal to L in this expression, the second boundary condition, because this will be sine beta L, all terms will be there. So, this is equal to 0 because this the displacement at z is equal to L is also 0. So, this is second equation. Now, we will apply this boundary condition for moment. So, this is the same equation for moment, because we need double derivative of this function. So, we are taking double derivative of this with respect to z. So, we will get this if we differentiate with respect to z twice, and now we are substituting this particular boundary condition here. So, we are keeping z is equal to 0. So, first term will be 0, third term will be 0. So, basically if we simplify this equation, now we will get minus C2 plus C4 is equal to 0, and the last boundary condition, this one, if we substitute, we will get this equation. So, basically we have 4 equations, that is first equation is this one, second is this one, third is this one, fourth is this one. So, these 4 equations contain 4 unknowns. So, we can able to put them in this particular form. So, all the unknowns I am keeping here. So, basically I have rearranged those equations, 4 equations in a matrix form, where unknowns are here and all the known quantities are here. And we have seen that from the first equation and third equation we got this, and from these two we can able to see that these two conditions are only possible when both C2 and C4 are 0. So, if both C2 and C4 are 0, if we put this here, this equal to 0. So, basically you will see that from second and third equation, from fourth equation, second and fourth equation, we will get this, because other equations will be 0, they will not contribute anything. So, from second and fourth equation, after putting this equal to 0, that means C2 is equal to 0 and C4 is equal to 0. This will reduce to this 2 by 2 matrix, where C1 and C3 are unknown. Now, if we take the determinant of this equal to 0, we will get a equation like this. And this particular equation, we will see that this all terms beta, sin beta L and sin h beta L is one solution common, that is beta is equal to 0. But beta cannot be 0, otherwise we will be having trivial solution. For non-trivial solution, beta we need that should be non-zero, and for non-zero beta we can able to see that this will not satisfy this, and the first term and the third term will never be 0 if beta is not 0. So, that means we need to have sin beta L equal to 0 for the condition that we do not have beta is equal to 0. So, basically we are getting a frequency equation from this. This is the frequency equation, and the sine function is having infinite solution even when beta is not 0. And now, so this is the solution. So, this is the infinite number of solutions which is possible, for which sin beta L is 0. So, if we substitute this for all, we can able to get the these values. This is equal to 0 value. So, you can able to see this is the frequency equation, because we related the beta with the natural frequency earlier. So, beta square we related with natural frequency earlier. So, that expression we can able to see here. This expression. So, from that we can able to relate the natural frequency, we can able to get the natural frequency. So, this is the natural frequency where n is varying from 1 to up to infinity. So, that many number of solutions are possible. Now, let us see the same equation which we used earlier, this equation more carefully. If we take first equation of this, C1 sin beta L and C3 sin H beta L is equal to 0. Now, first term, for we are considering when beta L is not 0, that means this is a non-trivial solution when beta L is not 0. If you see the first term, this can be 0 for this condition, but C1 cannot be 0, may not be 0. And in this particular case, this term will be 0 only when beta L is 0, but for non-trivial condition that beta L not 0, this cannot be 0. So, C3 has to be 0. So, basically from this we are getting that C3 has to be 0 and C3 cannot be 0. So, that means in the whole assumed solution only C1 is non-zero, but C2, C3, C4 we have seen that all are 0. So, this will give us the eigenfunction. So, out of 4 terms only single term is left out, and this is the C1, and beta we have already obtained in terms of previously. So, that we can able to substitute here. So, this is the eigenfunction where n can be 1, 2, 3, 4, and this eigenfunction is nothing but the mode shape. We can able to draw the mode shape, how the beam will vibrate in simply supported case. Let us say for mode 1, that is n is equal to 1. So, n is equal to 1, this eigenfunction is giving us a half sine. So, mode shape will be something like this. For n is equal to 2, for n is equal to 2, we will be having full sine, or this will be at the middle. So, this is the node we expect, and for n is equal to 3, we will be having this. Similarly, if we increase various modes, this number of nodes will be increasing. You can see here it is 1, but here it is 2. So, we expect for every further increase in the mode shape, we will be having intermediate nodes in this particular mode shapes. So, this is a typical mode shape for simply supported beam, which we obtain from the free vibration analysis. Now, let us see the orthogonality condition. So, orthogonality condition, as we have seen in the torsional vibration case also, that because these eigenfunctions are independent of each other. So, if we integrate these two different mode eigenfunction by multiplying by this quantity and equate, if we integrate over the whole length of the beam, this will be 0 if these two modes are not same, and if they are same, then we will get some constant term which I am representing as m subscript m, which we call this as generalized mass in that particular mode, mth mode. So, small m is representing that particular mth mode. So, this is a generalized mass. Similarly, if we integrate the double derivative of this eigenfunctions, if two different modes, if two different modes are there, their integration is 0. If modes are same, then we are getting a constant term, and this constant term K m we call as generalized stiffness in that particular mode, mth mode. Now, now let us see some other boundary condition and how the frequency equation and the natural frequency and eigenfunction take the shape. So, this is a fixed free beam, that is a cantilever beam. In this particular case, we have boundary condition that this is a fixed end. So, we will be having this equal to 0 displacement is 0, even we will be having prime of that, that means slope at this point will be 0, because fixed end beam will be having displacement and its slope 0 here. Similarly, here we will be having shear force equal to 0. So, we will be having bending moment and shear force. So, shear force, first let us say bending moment. So, double derivative at x equal to 0, and shear force is represented by triple derivative with respect to z, this will be 0. So, these are the boundary condition. So, we have 4 boundary condition as we had for the simply supported case. We can able to apply to the chosen solution to get the C1, C2, C3, C4 constants, and finally, on the same lines basically we will get this kind of function, this kind of equation. This is a transcendental equation. Earlier we had for simply supported case sin beta is L is equal to 0. Basically, this equation is the frequency equation, and roots of this will give us the natural frequency of the system, and if we obtain the roots of this is the natural frequency of the system, where beta is related with the natural frequency which we already seen. So, this is the natural frequency for cantilever beam case, and this for first mode and for this for higher modes. And eigenfunction is in this particular case more complicated, because some of the more terms of this constant C are non-zero. So, this is the eigenfunction, and if we plot this, we know that the mode shape for this particular case, let us say for n is equal to 1, if this is the center line, we will be having because at this end we have slope and linear displacement 0. So, while drawing the mode shape we need to take care of that. So, first mode will be something like this, where we can able to see displacement and slope. If we draw the tangent here, that will be along this, that will be 0, and second mode, in second mode also that particular condition we need to satisfy, but we will find another node here. So, this is 0, but we will be having one node which will be appearing here. So, basically during oscillation they will be having oscillation in other extreme in this direction, or this will be having vibration like this. Third mode, then we will be having another node here. So, that can be extended for, so this for n is equal to 2. For higher modes we can able to draw the mode shape on the same lines. Let us see another boundary condition, that is when both end of the beam is fixed. So, in this particular case we have displacement and slope 0 at this end, and here also the same condition is there at z is equal to L. So, now we have again 4 boundary conditions. We can able to obtain the 4 constants from the chosen function, that is C1, C2, C3, C4. We will get a frequency equation like this. This is the frequency equation, which is transcendental equation, and solution of this will give us the natural frequency, and this is the eigenfunction, because we can able to, once we are obtaining the C1 to C4, eigenfunction will be in the explicit form. Now, we can able to plot this and we can able to get the mode shape out of this. So, I am not drawing that particular shape. So, we have seen that how we can able to obtain the governing equation, and if we have different boundary condition, how we can able to get the frequency equation, like for simply supported case we have given the more detail how we can able to get the frequency equation. Generally, in the frequency equation in this particular case is a transcendental equation. In previous case we found that this particular frequency equation for discrete system is it is a polynomial form, but here now it is a transcendental equation which is more difficult to solve. And apart from that, we have seen that the natural frequency are infinite in number, and corresponding the eigenfunction or the mode shape is also we can able to obtain. And once you plot them, you can able to see that each and every point on the beam that shape is defined here. As we know that eigenfunctions are not unique, their shape is unique, but not the size. And now we will see that what these natural frequency and mode shape, how we can able to use it for the forced vibration. We already seen the orthogonality condition that these particular modes are orthogonal to each other. So, this particular property which will be using it for the forced vibration analysis of such system. So, we will just outline the method how it can be applied for the forced vibration. So, this is now we are trying to solve the forced vibration. So, this is the governing equation which we derived earlier, in which now we are considering the forces also. This is a distributed force and this is the concentrated force. Solution of this, now we are assuming in a form of the eigenfunction and a harmonic function. In this particular case, this is basically eigenfunction which we obtain from the free vibration analysis, and we know that this eigenfunction are infinite in number. So, we are assuming here whatever the force response which we will be getting will be basically summation of various modes of the vibration multiplied by some constant, because in this we will be having initial condition constants in the nu. So, basically here what we are assuming that any response, any force response can be represented by summation of various modes eigenfunction multiplied by some constant, initial condition constant, and this is generally this is similar to the Fourier series. If you think of a Fourier series in which we represent the periodic function as a summation of sine and cosine terms and some constant term. So, basically and their higher harmonics. So, we represent a whole periodic function by summation of various terms, and depending upon the accuracy required, there we truncate the series up to certain value, certain terms. So, similarly here you can expect that when we want the solution, approximate solution, we need to terminate this particular series up to certain value depending upon the initial condition. So, let us substitute this assumed solution in the equation of motion, and then we are multiplying that particular equation both sides by a eigenfunction which is, let us say, x k, which is other than the x I as such. So, this x k we have multiplied throughout, and then we have integrated over the domain. So, that means first we are substituting the assumed solution, multiplying by another eigenfunction x k and integrating over the domain. So, you can able to see this particular term is belonging to this one where we have substituted this. So, once you substitute this here, the fourth derivative with respect to z will come here, this is not a function of z. So, this will be separate. We have multiplied by x k also and integrated over domain, that means dz. Similarly, this is the second term, this term, in this derivative will go into this function, and this is directly multiplied by x k and integrated over domain. So, now you can able to see that earlier orthogonality conditions we had, that if these two are not same, integration of this will be 0. So, that means in this whole series when I is equal to k, then only the terms will be non-zero, otherwise they will be 0. So, out of all infinite terms, only one term will be non-zero. So, let us say that is a particular term is I. So, from previous equation, basically here you can able to see this will be having some value. So, we are getting this one. So, this is this term, and we already seen that this particular term gives us the generalized stiffness, and this term gives the generalized mass, and here we have simplified them. Even we have divided by generalized mass, so that this omega n of I square is represented like this, and this is the integration of that particular force. Here we have not done any change. So, I have just represented F I as this. Only thing is, because we have divided the whole equation by generalized mass, so this is also appearing. So, you can able to see generalized mass, stiffness, this is the natural frequency of that particular mode. So, here this particular equation which we obtain here for one of the x k, but x k can vary from 1 to infinity. So, that means such equations will be getting infinite number of equations, but this equation is, if we see carefully, this is a equation similar to the single degree of freedom system. So, basically what we are doing here, this is, we call it model analysis. In this we have a system, a single system, and is having infinite degree of freedom. Using model analysis, we have converted this single system to infinite systems, and each system is having 1 degree of freedom. So, this is model analysis. So, now you can able to see this is simple to solve because this is single degree of freedom system. This particular force is more general in nature. If it is harmonic force, then the solution is straightforward, but if it is more general aperiodic function, then we need to solve using the Duhamel integral or convolution integral, and this is represented by this integral. And in this you can able to see this is the force, and these are the initial conditions of the problem. These are the initial conditions. So, we can able to, depending upon the explicit form of this function, we can able to get this particular term. And once we got this, we can able to substitute this in the initial assumed solution, and that will be the force response, because this we already know these are the eigenfunction which we obtain from the free vibration. So, in today's lecture we have briefly outlined the continuous system approach for the transverse vibration of beam. In this particular case, we have considered the Euler-Bernoulli beam, which is most simple beam, and very simple boundary conditions like simply supported case we have explained, and how to get the eigen frequency equation, natural frequency, mode shape from the governing equation we described. The idea of this is that we can get the solution of the differential equation, partial differential equation for simple boundary condition, but if we have multiple supports and some more number of discs in the shaft along with the distributed property of the shaft, we may find difficulty in the solution of such partial differential equation. So, and in this particular case we will be having the finite element method, which will be helpful. So, in the subsequent class we will be exploring how this continuous system approach can be approximated using the finite element method, and then we can able to have the advantage of the continuous system, that is a distributed property of the system, and even the more complex boundary conditions we can able to handle with the finite element method. So, now after this 2-3 lectures will be devoted to finite element analysis of the transverse vibration.